Welcome everyone. I am absolutely thrilled to have you here today. In this explainer, we're doing a highly focused, highly visual deconstruction of one of the most pivotal breakthroughs in computer vision, the core mechanics of Yolo V1. Before we can really appreciate the bells, whistles, and massive architectural upgrades of the newer versions, we've got to build a rock-solid foundation first. We need to understand exactly how this model looks at a scene and translates what it sees into pure, actionable mathematics. Okay, let's dive into this. Here's our structural blueprint for today. We'll start with the single-pass revolution, then look at dividing the image grid. From there, we'll jump into the 5-value vector, understand normalizing the dimensions, and finally, wrap up with scoring the objectness. Basically, we're zooming progressively from the whole image down to the underlying mathematical formulas.
All right, kicking things off with Section 1, the single-pass revolution.
To truly appreciate this, you kind of have to understand how things used to be done. Before YOLO, models would essentially scan an image piecemeal, right? Just looking at tiny patches over and over again to guess if an object was hiding there. But this model treats detection as a single regression problem. It looks at the full, intact image one time in a single pass and predicts the bounding boxes and the class probabilities simultaneously. By doing this, it doesn't just see a coffee cup, it sees the coffee cup in relation to the notebook, the desk, and the apple. It gains this incredible contextual awareness of the whole image at once, which is exactly why it can operate at real-time speeds for things like self-driving cars.
Moving right along to Section 2, dividing the image grid.
Let's look at how the model initially prepares the physical space. Notice the everyday objects we have on screen. There's an apple, a coffee cup, and a blank notebook. The very first physical step the model takes is standardizing this canvas. It takes the entire image, no matter its original aspect ratio, and resizes it to exactly 448 by 448 pixels. This ensures that every single mathematical calculation that follows begins from the exact same starting line.
And this brilliantly illustrates the next crucial step. The model applies what we call the S=7 framework. It lays this 7 by 7 grid completely over our objects, slicing that 448-pixel canvas into 49 distinct operational zones. The image is no longer just a picture, it's a highly structured matrix ready for analysis.
I want you to imagine each of those 49 grid cells as a highly specialized, absolutely ruthless security guard. Their sole jurisdiction is triggered if the absolute center of an object falls within their specific square. Now initially, each guard or grid cell is allowed to predict 2 potential bounding boxes for that object. But the model doesn't keep both. It immediately compares their confidence scores and aggressively filters out the weaker prediction. Only the one single box with the highest score is retained. It's survival of the fittest right at the grid cell level to find the one true boundary.
Let's zoom directly into the brain of a single grid cell now in Section 3, the 5-value vector.
Now, what's really interesting about this slide is how simple the model's final communication becomes. When that grid cell makes its ultimate prediction about our coffee cup, it doesn't spit out a complex paragraph. It outputs a clean, highly efficient array of exactly 5 numbers, X, Y, W, H, and C. Everything the computer needs to know about that cup is contained right there in that array.
Let's briefly cement this definition so we all understand the translation from visual bounding boxes to pure numerical data. The 5-value vector is a mathematical array. X and Y pinpoint the exact center coordinates, W and H determine the physical dimensions, and C tells us the prediction reliability. Is that straightforward?
Which brings us to Section 4, normalizing the dimensions.
The secret here is a clever tale of 2 different scales. We've got hyperlocalized math to find the center and macro-level math to draw the outer boundaries. Specifically, the X and Y coordinates are normalized locally based only on the specific grid cell size of 64 pixels. On the flip side, the width and height of the bounding box ignore the grid entirely and are normalized globally by the entire image's overall width and height.
Let's move to and see how this builds visually. Notice the blue dot right in the center of the coffee cup, and look at the arrow pointing from the top left corner of that specific grid cell. That corner is the cell's origin. X and Y don't care about the rest of the image. They act strictly as positional offsets from that top left origin. They anchor strictly to the corner of that specific coffee cup cell.
But now, shift your focus to the blue brackets, defining the full width and height of the box. Notice how they break completely out of that single grid cell's jurisdiction. The coffee cup is bigger than one cell. So, to calculate W and H, the model uses the scale of the entire image canvas. It measures the object's total footprint on the global stage.
Let's transition to the final and arguably most critical piece of the puzzle in Section 5, scoring the objectness.
So the crucial point is this final variable, C. It represents the bounding box confidence score. All of that beautiful, elegant math we just did to find the x, y, width, and height means absolutely nothing if the C variable doesn't actually believe an object exists there.
You'll often hear this referred to as the objectness score. It is a strict probability metric that answers one question: how confident is the model that there is a genuine, physical object inside this specific bounding box? This single number acts as the ultimate quality control, ensuring the model doesn't just hallucinate boxes on an empty desk. If that score is low, the vector gets trashed. Think about what we've covered today. This model took an image, sliced it into 49 cells, forced them to compete, generated localized and global bounding boxes, and strictly graded its own work, all in a single lightning-fast pass. It fundamentally changed the game. But it leaves us with an incredibly exciting question. If Yolo V1 achieved this level of contextual mapping in a single pass with a basic 7x7 grid, what massive architectural upgrades are waiting for us in Yolo V2? I highly recommend you keep that question in your back pocket as you continue exploring this space. Thanks for joining me on this explainer today.